I'll just share that. Just last meeting I shared that same file, but okay, I'll do it again. I'll just put it in the chat box. Okay, you can copy it. Okay.
Yes, sir, got it. Thank you.
Mhm. Okay. So can somebody tell me, like, if you have went through the lecture, can you tell me where can we use this concept positive definiteness? For which type of matrices we can use this positive definiteness or the definiteness? How will we find for which type of matrices can we know regarding the definiteness of the matrix or how that matrix will behave if we are writing that matrix in the function form? Or maybe how will we know regarding the for which type of matrices can we say anything about the behavior of that matrix?
So, sir, can I answer?
Yeah, sure.
The corresponding function should be positive at all x and y's, and its stationary point should be at 0.
Okay, so this we are saying for positive definite, huh?
Yes, for positive definite.
Okay, I'm just asking for which type of matrices can we know regarding the behavior of this matrix? I mean, there is a set of matrices for which we generally do this functioning. So for normal, yeah,
Symmetric matrix. Symmetric
yeah,
matrix.
yeah, for real symmetric matrices, generally we do this. So if you are getting uh, for non-symmetric matrices, there can be some other method, but this method is not applicable there. Okay, whatever we are discussing in this lecture. So this is totally for the real symmetric matrices. Okay. So this is the first important thing. If you are getting any questions regarding those matrices which are not symmetric, for those you can't use this methods, whatever we are discussing today. Okay. So that's the first important point. Okay. Okay. Can somebody tell me how generally you convert matrices to a function if you have been given, sorry, a function if you have been given, how generally you convert that to a matrices? Is there any method that you know how we generally write this? Like, okay, this is the one way. This is a like hit and trial method that you wrote this function in a matrix form. Okay, I'll just
Sir,
yeah.
I think the coefficients of the quadratic term would be in the diagonal part,
Okay,
and the coefficients of the cross terms, that is x, y, that would be in the off diagonal part.
but here it is 2b, right?
Sorry?
Here it is 2b, right? This
Yes,
a and b
here
is
it is two.
fine. That will come in the diagonal, uh, like
So,
diagonal
like
element. Hmm.
half of the coefficients of x and
Hmm.
y's, I think, would be
Why
in
the
the.
half will go here and half will go here?
Right. Symmetric, na? So that's
Yeah, because it's a symmetric matrix, so half of that will go. So that's the one method. So the first method is hit and run that we have told. So it's a hit and run method. But if you need to know regarding the like from this matrices for any function that have been given to you, and if you have been just asked to write the just write the matrix, okay, then only the hit and trial method can be used, okay, to write the exact same matrix, okay. But if you have been given the function and if you have been asked to know regarding the behavior of that matrix, that will be from the same function, okay. So on those cases there are some methods from where you can conclude to the Hessian matrix, okay. And the Hessian matrix, whatever the function you have been given, like for example this is a function, you can conclude to one Hessian matrix. Okay, Hessian matrix, I'll discuss how generally you find the Hessian matrix. and the behavior that the matrix, this Hessian matrix, will show according to corresponding to this function. Uh, so will be the same behavior of the exact same matrices that we'll get from this function. Okay, so that's the one thing. Like the Hessian matrix that you'll get from this function will behave in a similar way uh, to the exact matrices that you'll get from this function. Okay, so the Hessian matrix I'll discuss it later, but that's the one point I told you. Okay, so the first point is to conclude to the same matrices from the function, you need to, the heat and trial method is the one way that you can use. Okay, so like for example here it has been used. So whatever was the coefficient of x square and y square, you wrote in the diagonal element, and 2b was there, so half of you have to write because it's a symmetric matrix, so it will get added whenever you will do the what is it, do the multiplication, and we'll multiply that and equate it to the function, you will get the value. That's the one method. So if you have been given any value, you can just write, like for example, if you have been given 3 cross 3 also, like it's a function that has z square also. So what you can do, you can just write ABC, and you can, like you can just expand that matrix and can equate it to the values and can get the value of A, B, C, D, like whatever there in the 3 cross 3 matrix. That's a difficult one, but yeah. So if you have been given to write the exact matrices, that's the one of the methods that I know. There can be some other method that I'm not aware of that. So I generally use the basic approach, that is the hit and drag. That if you have been given the option, you can directly mark. But if you have to write the exact same matrix, that's the difficult one. But if you have been asked to know regarding the behavior of that matrices, then I can give you a very simple method to know regarding the behavior of that matrices. Okay, that is the Hessian matrix that generally we do. Okay, so we start with the function. This is the function, the basic function. The quadratic form we can write in this way. That I told you. This is just the notation because it's a V transpose A and V. Okay, yeah. So the first thing is, how generally you get the stationary point? Can somebody tell me how generally you get this basic maths problem? If you have been given a function, how generally you get the point where the slope generally gets zero?
Derivative of that function should be 0.
Yeah, you just equate, you just calculate the derivative of that function and see that for which value the derivative is zero. Okay, derivative means like the tangent is zero, the slope is zero at those points. Okay, so this is what generally we do here also, because we have the two variables x and y, so we are differentiating, partially differentiating that function. So like one with respect to x and keeping the other variable constant, and then the differentiating the function, same function with respect to y and keeping the x as constant. Okay, okay, so that's the basic approach to get the stationary point. Like if you have got like two functions and then equate it to zero, if you'll just solve, because you have two variable and two equations, you will solve, you'll get the value of x and y. That's the x and y, where the function, like whatever the values you are getting, that's the stationary point. That like that the function is the slope of that function at that point is like zero. From there it can be like, and then if you are doing the second derivative, that will help you to know regarding whether this function is having maxima or minima point at that point, because the plot can be like this also, it can be like this also, it can be some other like values also. Like for example here, this is stationary point, the slope was zero at this point, here also the slope was zero, and for this case also the slope is zero. But for this point, the minima is there, and for this point the maxima is there, and for this point we can't say whether it's a maxima or minima, because for some points, like if you see for the x positive, it is going upward, and for if you are seeing for x negative, it's going downward. So in this side it's like it will behave like a maxima, and for this point it's behave like a minima, so you can't generally say about anything about this function. Okay, so this is the basic like approach how to get, like you have to differentiate, partially differentiate those functions and then equate it to zero to get the stationary point. Okay, so this is the determinant that everybody knows, I guess, how to write the determinant. Like see, this is the simple Hessian matrix that I was talking about. So this is simply the Hessian matrix. So this generally help us to know regarding the behavior of that matrix corresponding to that function. Okay, So if you have been given 2 cross 2, how will you do that? Like you can write it like this. Whatever the function you have been given, some fx is given to you, fxy, right? So what you have to do here, you need to differentiate with respect to x and then y. Here also x and y. So here you need to differentiate with respect to x and then again with respect to x. So here you need to differentiate the function twice, right? So 2f by dx square. Here you need to differentiate the function with respect to y and then with respect to x. So whatever you are like good with, like you can differentiate with respect to x first and then y. So whatever the function or whatever the matrix you will get, it's not the exact matrix that you are getting, but you will get the similar matrix, okay, corresponding to that function, and it will behave like the matrix. Whatever you are getting will behave in the similar way as the matrix, uh, that is corresponding to that function. Okay, so this generally helps you to get the behavior of that matrix. Behavior, I mean, behavior means that how does that function will behave, with like it's a positive definite or it's a negative definite or it's a semi-definite or indefinite. So the behavior generally tells the Hessian matrix will help you to get the behavior of that matrix. Okay, and if you have been given the exact matrix, you can directly say, but if you have been given the function, then you need to get the Hessian matrix. Okay, even there are other methods also that I'll discuss, but the Hessian matrix is the basic. If you have been given the 2 cross 2, you can directly calculate the Hessian matrix and can see whether AC is less than B square or more, or it's equated to 0. Okay, so there are methods. So this is the one like basic simple example, like not example, the basic properties. Like if you are having the stationary point and the condition is this one. If the A is positive, if you have been given the function A s square plus 2xy plus b square, okay, by square. Okay, so in the class 12th, maybe you would have read, like whenever the A is positive with this x square, you can see that this function generally goes upward, right? So at this point, the stationary point will start behaving as a minima, right? If it is a negative, A is negative, then this function will be like this. Like in the quadratic equation also you would have read y square, like what is the equation of the quadratic equation? Y equals to what? Y equals to 4x. This will be a parabola. If you are equating x square is equal to 4ay, this will be like this, right? So if you are having the x is positive, sorry, the coefficient of this x square is positive, it is going upward. Okay, that means the stationary point is minima at that point. And if this is a negative value, then it's a maxima at that point, because this is a inverted ball. You can imagine that as an inverted ball. Okay, and for the saddle point, that means like the determinant is negative, but the point is it's a like so this type of plot, like for some values, if you are checking for x positive, it can be go up, like the values next to, for if you are increasing the value of x, maybe the function value can increase, and if you are decreasing the value of x, then maybe the function value is negative. Okay, those are generally the point for which you can't generally say like whether how the function will behave. Okay, or maybe for those points, the saddle point, like maybe uh, the second test, whatever you're calculating, second test means the second derivative, whatever you're doing, you're getting the zero there at those points also. Okay, and whenever the determinant is zero, that is inconclusive. Like you can't say anything about that because you don't have much data to say anything about that. Okay, so this was like the basic things about, like if you have been given the function, then how can you say about the stationary point? How can you find the stationary point? How can you say that whether those stationary points are minima or maxima? Okay, that's the one thing. And now we are dealing with the whether this function, whether the matrices, whatever, or the function that has been given is will behave like a positive definite or the semi-definite or the negative definite, or it's an indefinite function. Okay. So there are various methods to know about the definiteness of the matrices, but the basic and the very simple method is to calculate the eigenvalues and to know whether how what's the like sign or sign of the eigenvalues of those matrices. Okay, if you are getting the one of the basic method is this one. These are also the main like this also given to just define those matrices to get the properties of those matrices. But the basic method is the very basic method is this one where it's spent. Okay, this also okay. Like for example, if you have 2 cross 2 matrix, then this can be a useful method. Like this method can be useful if you are getting 2 cross 2. But if you are getting more than 2 cross 2, then it becomes very difficult to calculate and get this from this approach. Okay, for this, if you are getting 2 cross 2, then you can directly say, see, if you are having 2 cross 2, then you can directly say if A is positive or and the determinant is positive. Like what happens, this can be useful for the 3 cross 3 matrices also. But what you have to do generally, if you have been given A, so whatever the matrix you have been given, so what you have to calculate, the first method I am telling you to calculate the eigenvalues, okay? And there are some conditions for the eigenvalues also. Like the first condition is if all the eigenvalues are positive. Positive means greater than equal, not greater than equal to zero. It should be greater than zero. Like none of the eigenvalues should be equal to zero. Then it's a positive definite function. So this is the first like thing. If all the uh, eigenvalues are positive, then it's a positive definite function. And if you are getting some of the eigenvalues as equals to zero, like one you got eigen, so if it's a 3 plus 3 matrix, and if you are getting one eigenvalue as zero and the other eigenvalues as greater than zero, then it's a semi-definite uh, matrix. Okay. And if you are getting some of the eigenvalues as negative, like not some, if all you are getting as negative, the eigenvalues, then you can say it's a negative definite function. And if you are getting some as zero and some negative, then you can say semi negative, like what you can say, semi negative definite function. Okay. So there are 4 or 5 things that I have written in the one slide. I'll just say that one also. So it's clearly written there also. Okay. And this method can be useful if you are having 2 cross 2 matrix only. So this method can be helpful for you if you are having 2 cross 2 matrices only. So what's the like the definition? So A should be greater than 0. A is greater than 0. That means it's going upward, and then the determinant is greater than 0. Then it's a positive definite function. So this will be upward ball. You can imagine that as a upward ball, and the positive semi-definite function where the function is greater than or equals to 0, or you can say the eigenvalues should be greater than 0 and some can be 0 also. Okay, there the determinant is equals to 0, determinant is equals to 0, and the A is positive. So it's also upward ball. It's not a ball. You can imagine that as a valley. Okay, and the upward valley. But for some values, the for that valley, you can imagine that as a valley. Valley generally has a plane of values where the values would be 0. Like you will be having a plane where the values would be 0. Okay, but here you can imagine this positive definite as a ball. Ball generally have a single point where the value is 0. But for this valley, there are a large chunk of values where the you'll have a plane where the, like you can imagine this as a this value. How the draw like this, the folded paper you can expect the folded paper, and the folded paper is like this. Okay, so for that, for
Yeah, like
the
construction pipes,
huh, yeah,
which are lying
pipes
on the
you can
ground.
expect. Yeah, correct. Pipe and half cut pipe, or maybe the bamboo that is half cut. So those cases you can expect as the positive semi-definite. Negative semi-definite, where the function value is negative, or you can say the A is negative, but the determinant is positive. Okay, or or you can say the eigenvalues are negative for those cases. Semi-indefinite in the same way, only the difference is where the function is negative, where the function is inverted. Like you can imagine this semi-indefinite as the inverted form of this. Okay, where the A is negative and the determinant is 0. And indefinite is like wherever you are getting the determinant as negative, then you can say indefinite function. Okay, for those functions you can't say much about because you don't have much information. So this is the first example of simple basic. Okay, till now if you have any query you can ask.
No, sir.
Okay.
This table we need to memorize.
Yeah, I'll share this file also. I'll upload in the same thing. I have written somewhere also. Here also I have written. Yeah. So here I have written everything. So this also you can just share this file also. It's a like basic. So these are the three methods generally we use. Okay, to calculate. There are other methods also. These are the very basic method that you can see. So the first method, so every time, this is I guess the most simple and the most accurate one. If all the eigenvalues are positive, then you can directly say it's a positive definite. Similarly, you can see for like this is a positive definite, so all eigenvalues should be greater than zero. And for like semi-positive definite, you can say eigenvalues are like greater than equals to zero. Then similarly for all the other cases, you can imagine pivot value greater than zero, like if you are converting that into a reduced row equilibrium form, if all the pivot values are like greater than zero, you can directly say. Or there is one leading, if you are able to calculate, like for example, here it is A1, A2, A3. Just imagine this is a real
The
symmetric matrix
pivot
where if,
values, pivot values will be greater than zero only, no?
yeah,
No, I mean, could it be
so
so like it is less than zero? I mean, we generally make it one.
yeah, we generally make that as one. Okay, I guess there is some confusion in this. No, pivot, yeah, pivot value, you are correct. Pivot value is generally greater than zero only for all the cases. Uh, mm, okay, I need to check this one. What is written? I wrote this, I guess, 4 5 months back, so I can't remember what I wrote there. Okay, that I need to check. So pivot values in here, correct. Pivot value is also positive. I guess I was writing the something else that I'll show you now. So this is A8, A9. Okay, so imagine this as a symmetric matrix where A2 is equals to A4 and A3 is equals to like whatever the condition we'll get from here. So imagine this is a symmetric matrix. So if you are able to calculate, so if you are the leading values means the leading determinant. If all the leading determinant are positive, you can directly say it's a positive definite. Leading determinant means okay. So what I was referring here, this pivot value, I'll tell you what I was referring here. So for this, if you are having A1 as positive, and then leading this one, then leading determinant means the first after calculating, if you are having 3 cross 3 matrix, first calculate the determinant of 1 cross 1, then the determinant of 2 cross 2, and then the 3 cross 3. If all the three are positive, we can say this is a positive definite. Okay, and but for the positive semi definite, for the negative definite, there are other conditions. Okay, this can be helpful if you are directly able to see, if you are able to directly calculate the leading determinant, and if all the three are positive, then you can directly say it's a positive definite. Okay, so pivot value, what I was referring here is this one. So if you are calculating the leading determinant like here A1, and the leading determinant of this one 2 cross 2, what is that? A5 into A1 minus A2 into A4 divide by A1. This I was referring this pivot values. Okay, so I don't know what I need to write, but maybe I read from somewhere. So this I guess I was referring. If this is positive, so whatever you are calculating, like for example, you have calculated the 2 cross 2 determinant value, and if you are dividing with this A1, okay, and that is also positive, A1 is also positive, and again the determinant of this upon whatever you are getting here, that is also positive, then this matrix is a positive definite. It's a bit complex one, so that's why I was saying the very basic and very simple is to calculate the eigenvalues. And if you are able to calculate the eigenvalues, the sign of the eigenvalues only can help you to get the character or the detail of that matrix. Okay, so this pivot
Till
thing.
it is 3 cross
I,
3, calculating eigenvalues is okay.
yeah,
Hmm.
no, I was reading somewhere. These are called leading principal minors. If these are positive,
Okay.
then it's definitely positive. If they're alternatively positive, मतलब one is positive, next is negative, then positive. If that
Yeah.
trend
Then
continues, then it's definite negative.
yeah. So this is what I was saying. So then, so for the positive definite, it's a simple, but for other cases, it becomes complex. Like this
Yeah.
is a positive definite one and one that I don't know. Maybe I guess you are reading from Gilbert. I think so. In Gilbert only it's written Like if you are having some odd number of positive and then even number of positive, those sort of things are there. So I thought, okay, it's like very confusing. So it's better to go with the eigenvalues. Or the other method is the power, to calculate the power or the maybe the area under that is the also one method that I read from the Gilbert. But that also is not going to help you most in most of the cases. So it's better to go with eigenvalues or the principal, whatever you were saying, minor. What was the term used? Principal?
It's called principal minors.
Okay,
Or the
principal
leading
minor.
principal minors, like you said, leading principal minors. So
Yeah.
A1, then the next minor, then the full determinant.
Okay. Okay, so that's the one approach. If this is a positive difference, you can directly say. But for other cases, if you are getting some as negative, then again I need to like you have to, whether if you are able to remember those cases, then it's fine. But if you are not remembering, then you can go with this. You can calculate the eigenvalues and can directly say. So this method will help you every time. Okay, and I guess this is the one of the best also.
Sir, but with the Hessian matrix itself, we can also determine whether it's semi-definite or definite or all these cases, no? Like without calculating the eigenvalues.
For the Hessian, if it is a 2 cross 2, you can directly say. But if it's a 3 cross 3, then also you need to first calculate the Hessian matrix. And then from Hessian matrix, you need to see whether the values are eigenvalues or not. Right?
I no, but for Hessian matrix, like there are conditions, no? If f11 is greater than 0, like you showed us that a
Yeah.
table.
That was for the 2 cross 2, right?
Okay, only for 2 cross 2.
Hmm.
Achha.
Hessian matrix can work for 3 cross 3 every time, like 4 cross 4 also. But the problem is for 2 cross 2, you can directly say, right? For 2 cross 2, if you have got fxx, fxy, fxy, and fyy, right? So you can directly calculate the leading. So this was the first leading, right? So this was A, right? So this is fxx only, fxx, and here you have got B, B, and C. Then you calculate the determinant. If determinant is positive, that means what? This is what we are doing here also. We are just calculating the leading determinant, right? Leading minor factor, whatever the term is. So 1 cross 1 we are calculating, and then we are calculating for the 2 cross 2. So this is the same thing we are doing here also. And in the conditions also, we have written A should be positive and the determinant should be positive. The determinant A is the first leading 1 cross 4, and the D is for 2 cross 2 matrix, 2 cross 2 determinant we are calculating. If both are positive, then we can say this is a positive
Okay,
vector, right?
okay, yes.
Correct? Yeah. And for 3 cross 3, you have to calculate, because for 3 cross 2, fxx, fxy, and fxz will be also be there. So you'll get 9 elements. Then you need to see whether eigenvalues, or you can go with the 1 cross 1, 2 cross 2, and 3 cross 3 thing also. But for 2 cross 2, it was very simple. You just have to see the what you can say, the coefficient of x square and then the determinant,
Okay,
right?
so
So
to
that's why it was
clarify,
simple.
if we have a 3 cross 3 matrix, and if we know that its
Hmm.
determinant is positive and the leading term fxx is positive, then can we say
Hmm.
that it's positive
Hmm.
definite?
No, you can't.
No?
No, you need to check for the other conditions also.
Achha, okay then, fine. Thank you.
Yeah. So like for example, so it's a 3 cross 3 matrix. Let's for example, you got this matrix 3 cross 3, something A, B, C, and some D, E, F, G, H, I. So for determinant, it's fine, and the coefficient also. So you got A as positive, and this also determinant as a positive. Then you need to see whether this matrix, the determinant or the leading determinant for this A, B, C, D, E is positive or not. If this is a positive, then you can say this is a positive definite. But if it's not, then again, I guess there
Achha,
are other
okay, I
conditions that you have to
understand
check,
now. Thank you, sir.
right? Yeah. Or it's very simple to go and calculate the eigenvalues.
Okay.
So eigenvalues will give you a good picture about everything. The sign of the eigenvalues. Okay. So I guess still now it's fine. Okay, this we'll be discussing tomorrow. No, okay, so yeah. So for example, there are some examples also. Like this is an example 4x square plus 4xy plus 2. Okay, can you solve this and can tell me whether which type of like what is the matrix, like this is the matrix, right? 4 2 2 4. So it will be a positive definite or what which sort, like can you tell me the behavior of this matrix?
Yeah, it's positive definite.
Okay, yeah. So it's
Yes.
clear, right? This 4 is also positive and the determinant is also. If you will plot like here, how generally do the now generally do like, this is for the stationary point. Okay, it's fine. Like 0 0 is the stationary point. You got this as the like partial differentiation with respect to x and y. So this was the example to just show how generally you calculate the stationary point, or maybe the how does like that behave, the point, how does that behave, because it's a positive definite, so you can directly say it's a minima, right? Because the positive definite will be something like a upward ball. So this point, the stationary point, will be a minima. So if you are able to see the behavior, then you can directly you can say everything about the stationary point and all the other aspects also. This is a plot for this matrix. This is a upward ball, right? This is also coming upward and this is also coming upward. This is a positive definite function. Okay, what about this matrix x square minus y square?
No, the C term is negative.
This is the this is the
This will be
it's a saddle point. You can't say much.
So I think we can't conclude.
It's a saddle point because the determinant.
determinant is less than 0, right? So this was the conditions, right? So 4 5 conditions was there. So for all the other cases, d was greater than 0. For saddle point, d was less than 0. So this is the last condition that we are getting. So d is less than 0, that we can't say much about this. And this you can see also from the plot also. This is the example, right? For the plot also you can see for some values like c, 0 0 is the stationary point. If you are moving in this side, you are getting this, the value of x is increasing. But if you are getting this side, the values of the function value is decreasing, right? So for this you can't say much about the function. Okay, so this was the basic stuff that was left in the 6th week. There are some other points also that I'll see at this chat.
Is there a form? Is there a way of deriving the quadratic function for when it's 3 variables? Is there a standard form?
From the matrices or from the function to matrices?
Like from the function to write the matrices.
Okay. So the exact method, there is no exact method, only the hit and trial can work. But to get the behavior, you can calculate the Hessian matrix.
Okay. Okay.
So Hessian matrix, you know, right? How to calculate?
Yeah. That we know. Taught in
Okay.
maths too.
Yeah. So then the behavior you can directly conclude whatever the Hessian matrix will behave, the similar behavior will be for that matrix.
Okay.
Yeah. So there are some problems from the 6, whatever we have seen the topics. So this is pretty like, it's not take more than 10 to 15 minutes also. So it's pretty simple. So x square plus y square, the stationary is 0 0. So can you tell me 0 0 is a minima or a maxima? And how does that how does that plot will be a
Upside.
upward ball, right? Upward ball. So this is the function. Okay. And how does this behave? Minus x square minus y square. Okay.
I think it will a maxima.
Yeah, maxima, and the behavior will be like this, right? So what about this x square minus y square? I guess we have discussed this, right? X square minus this we can't say. Like the function, you can't say much about this. This is a saddle point. No. Okay. What about this x minus x?
Still negative, no? Still a saddle point.
Then we can't conclude. Option D.
Yeah. So the plot will be like this. For some point, if you are just increasing the value of x in this side, so your plot is going, like the function value is going down. But if you are increasing that, like if you are coming out of your screen, the value is increasing, right? So you can't say much about. And for this is pretty simple. X square plus 12xy plus 10y square.
Sir,
What about this? What is the behavior of this matrix? Not the stationary point. How does it behave? This function. It's a
I
positive
think
definite function or a
I
what?
think it's a positive definite.
Positive. Yeah, it's a x is 8x square means it's going upward. And then if you are able to calculate the determinant, also you can directly say. You can see the plot. Okay, plot I have not plotted. Okay. What about this function? Can you convert this into a HN matrix and can say, okay, if, yeah. Can you tell me, okay, it's not been asked. Okay, this is a stationary point, then it's a pretty simple. You just have to do the partial differentiation and get the value. Okay, it will be this will be a maximum minima point, right? Because 8x square plus 2x square, it will behave like a what? Positive definite function. Positive definite means it's a upward ball, and upward ball means the stationary point will be a minima point, right? And for this cases only, we generally do the gradient descents and all. But this is why we are reading mostly about the real symmetric function. Because in the ML generally we work on this type of matrices only, matrices, or you can say the functions only. Because we need in the future we'll be doing this gradient descent, so gradient descent will be working for those cases, right? The upward ball. Okay, and whatever, this is a simple one. If what we are doing here, we are just inverting the ball, right? Okay, what about this 4x square plus 2xy plus 5 square?
I think again it's a minima.
It's a minima or
Saddle form. No, it won't be a. Mm,
see, this is a function. The determinant is less than 0, right? Because the determinant is what? AC minus B square.
Sir, can I ask one question?
Yeah, sure.
No, sir, where are you plotting these graphs and how are you kind of transferring it to PowerPoint or wherever, sir? Like, what software are you using? Is it Desmos or GeoGebra or?
This is a latex that we are using. Overlay.
Yeah, but the plot, sir?
The plot GeoGebra we are using.
Okay, plot is GeoGebra. Okay, okay. Thank you.
Yeah. So this was like because the determinant was negative. If you are getting determinant as negative, that's the only condition where the determinant will be negative. Saddle points are getting. So I guess, is there any other question that is difficult or anything? 3 cross 3 matrix, there will be, I guess, some, yeah. Okay, so if you are getting this type of matrix, can you say directly which type of matrix is this without even doing anything?
It's a positive
Positive,
definite.
definitely.
Why?
Because the eigenvalues are all positive. I mean, the
Yeah,
diagonals.
correct. Yeah, totally correct. Because the eigenvalues will be the diagonal element and it's all the positive. So you just need to get the sign, and if you are getting the sign, yeah. This for this, what is the value? You are getting eigenvalues as 0, 1, and 3. And what should be the character of this matrix?
Semi-definite, positive semi-definite.
Yeah, it's a positive semi-definite because some eigenvalues are getting as 0. There, this is the determinant is that we were talking like for each and sign. For this, everything is negative, so you're getting negative definite, right?
Yeah.
Similarly, for this also you'll get some as 0 and some negative. So it's the same in negative. Okay, this will be like study tomorrow. This is about the PC and all. For this like topic, I guess this topic was pretty simple, not much to like read or not much to discuss also. I don't think so there are any problem. Is there any problem in this topic? You can just ask.
So that Vishal or somebody said they've uploaded the video from yesterday, but I couldn't find it, sir. Where will it be in the live
Yeah,
session?
I'm Vishal only. So I just uploaded. Okay, so this is uploaded, and this we are getting. And the link also you can see in the calendar. I have uploaded the calendar also. In the calendar, you can just go. This is the link that you can see.
Got it, sir. Thank you.
Yeah, thanks a lot. And for today's session also, this is very small session, but I'll upload it after this after we are ending this session. So,
I don't know
because this
about
was
MLF, but in many courses it is not updated, the calendar YouTube links.
for our courses we have updated. I guess everything is updated. Like portal team, I'm not sending this mail to the portal team. I'm doing it by
Oh,
myself.
okay.
It's like so that it will get. Yeah, so I'm doing it from my side. So getting updated. Only maybe for the first week it should not be there because for the first week it's there in the like IITM online degree. So that also I need to download from there and upload it in this YouTube channel. Other than that, everything is uploaded, I guess, in our.
So, but everything is reflecting in the calendar, correct?
Yeah, everything is there in the calendar also. I've updated the YouTube link also for each and every video.
So for a function of three variables, how can we represent function in a matrix form?
Yeah, so the exact thing you can't do. So this is what I was talking for the exact matrix. You can't like you can do, but the
Sir, I think
method is the hidden
there is
drag
a
method.
question
Okay,
in
so like yeah,
assignment 6, question number 5,
okay, I'll just open that
6.
assignment. Okay,
Oh, no, sir,
practice, right?
graded.
Graded. If I'll open, I guess the answer will open. Okay, I'll just stop sharing and then question number.
Question 5.
Yeah, so this question, how you can do is one method is okay. So if you are able, yeah. So the one method is you can multiply, but that will take a lot of time. But what you can do is you can see some of the values, right? Some of the values means okay. I'll just so okay. So for some of the values means see for this question, this is the question, right? Fifth one.
Yes, sir.
Now, if you are able to calculate the Hessian matrix, if you'll calculate the Hessian matrix, you can get the behavior. But if you calculate, it will be mostly like generally we get the Hessian matrix in the form of some multiplier. Okay, but for this case, how will you do? Like for example, x square plus if you are multiplying, you can see that first it should be a what it should be 1, and then if you are getting xy as minus xy, where is that? The only method I can see is to multiply and get the values.
So
Okay,
we
the
have to
other method,
multiply all the
yeah,
equations.
or all the equation you need to multiply, and maybe some smart work can work here to see some of the coefficient, like because if you are multiplying also you are just getting the coefficient, right? say for example x square to the first. Okay, so see the first, this option is incorrect only because if you're getting -1 here, so this would be like minus x square. So this option get cancelled from here itself. The now you're left with three options, right? If you see for the z square is -1. Okay, for all the three cases it should be -1. Okay, and again if you're
I think
seeing
the
some
same
what?
question in practice. Same question in practice assignment. So is there we have solution for the practice
Yeah,
assignment?
we have the solution also will be same. I only have solved some of the problem. You can see where I've solved. Where is
So what I
ML at
realized is
100?
the diagonal elements have to be the coefficients of x square, y square, z square.
Yeah, because if you are multiplying, you'll get yeah, correct.
Yeah. So from there only two of them remain. That is first option and third option.
This is oh, yeah. So where is that? Okay, okay. I can open that one. So fifth problem, right? Okay. So here also you can see this x square minus z square, right? So y square you don't have anything. I guess D should be the correct option, right? See, why D is the correct option? Because see, y square, if you are doing the calculation, because here y there was no coefficient for y square, right? So you should get 0 here, right? In between this middle value. If this middle value is 0 for this case only, right? You can directly say this.
Yeah, so even if it was not like this, if we had this like in the graded one, it will come down to two options. After that, you multiply and then finalize. But you can't like beyond
Huh.
that point, you have to do some computation.
Okay. Try the Hessian matrix also. Maybe the Hessian matrix will be, I guess, in the multiple of some values because it behaves in similar way, right? It will be like a multiplier or but this is what I will tell you. If you are getting some problems, better to multiply. Like some options you can directly eliminate, but for if you are getting stuck with two options, then for this problem it's pretty simple because y square was 0 and you can directly say this is for fourth option. What was the question number? Fifth, right? Sixth, which one?
Fifth one.
So I don't know where is that, but yeah, this is the problem, I guess. I don't know where is that. Practice assignment only. I've shared this file itself. 3, 4. Yeah, so this here also I've solved with this some trick only some. This is how generally we write, like, because we already know that this xy by 2 will be there and xy by 2 will because yeah from the coefficient it's like there's no like you'll get confused. It's better to do that the multiplication. But if you're having some tricks like here we worked like the y square worked for us. Like somebody told like you can directly see the diagonal element and if diagonal element will reflect you the coefficient of x square, y square, and z square because if you'll multiply that, you'll get the diagonal of those like diagonal element of the matrix as a coefficient of x square, y square, z square. Okay, so that's the only approach I guess will be there. Otherwise, you can try with the Hessian. Hessian will not give you, but Hessian can give you the behavior. So the only approach is to go with, I guess, multiplication or some smart work during the solution.
Okay, sir. So the
Because
another
I
question is
like last time also I found so many, like I was like googling here and there, but I didn't got any exact what you can say, the method to directly get the function. You have to do the hit and trial only, like ax square b, in some form just multiply and then compare with the values, then only you'll get the value of a, b, c, d, whatever the term, how many term you are having.
answer. How to find SVD, single value decomposition?
Those are very complex. Ram would have discussed yesterday, right?
Okay, so is there in session? Have
Huh?
discussed this.
Yeah. Yesterday, I guess he has discussed everything in yesterday's session. That's why we have splitted those sessions, because SVD is a bit complex one, and you need some like 1 or 2 hours to discuss those. That's why I told Ram to just go through the SVD part, and then I'll discuss the rest, because the rest part is pretty simple. So I'll post the solution also. I have some SVD handout. I'll just post that also. Maybe that will help you. I just downloaded, I guess, from some Chinese university I got. So maybe this will help you. This, this is a good handout that I read, the SVD part. This also I'll upload it. You can go through that. Okay, I'll upload this one. So for SPD part also, there are so many tricks to get direct values. Like you can calculate the eigenvalues or the singular values that you generally get, and then uh, the middle, the diagonal matrix can help you to eliminate some options. Because if you're just going and calculating the SPD, that's going to take a lot of time. It's better to use some tricks to solve that. Because in the exam, there won't be any problem to calculate all the SVD. All the problems that you'll get, you can directly eliminate on the basis of eigenvalues mostly, or the singular values that you generally calculate. To calculate the eigenvalue, take the square root. Or like for example, you can get some bigger matrix, like some matrix you can get like 5 cross 2, and the other matrix would be like some smaller one. Because generally what you do in SVD is generally calculate the what you do the transpose. Like if you are getting two matrices, you generally do the A transpose A or A transpose. So you should do that transpose. Like if you are having 5 cross 2, so what should you do? You should do A transpose A, so that you will get 2 cross 2 matrix, and then you have to calculate the eigenvalues for 2 cross 2 matrix, right? So if like if you are doing A transpose, that means you are calculating 5 cross 5 matrix and then calculating the eigenvalues. And for 2 cross 2 matrix also, you'll get the same eigenvalues. The other three will be 0. It's better to go and calculate A transpose A. You'll get 2 cross 2 matrix, then you'll calculate 2 eigenvalues, and other three will be 0. Right? So there are some tricks that you can use to calculate the SVD part also. Like just the diagonal element. And from the diagonal element, you can, I guess, you'll be able to eliminate the options. But if you have to calculate all the, like, for the graded and practice, you should calculate. But in the exam, you'll not get, for sure. But that I have seen the trend of the questions for the last 2-3 terms. There's no question where you have to go and rigorously calculate the SPD, like all the eigenvectors, and then you need to normalize and you need to write. So those cases will not get. And even like and for some cases, like pretty seriously difficult when you have to use if you are getting some repeated eigenvalues, for those cases you need to use the Gram-Smith method. Then it becomes more complex. Okay, so then for the graded practice, you can just practice 1-2 problem, and that handout that I'll share, there are 3-4 problems directly, like all the 3 types of problems are there that you can get in the paper, or maybe the normal methods that you generally do in the SPD. So there are 3-4 examples, all are of different types. You can go through that. But the basic thing that I've told you, whenever you're having a sum bigger, like 4 cross 3 or 3 cross 2, so it's better to go with such matrices. You just calculate the such symmetric matrices where you'll get a smaller matrices, and you can calculate the eigenvalues directly, and the other can be 0. So that will help you in a to calculate the SPD in a like quicker time, right?
Yeah, okay, sir.
Hmm. So I'll just stop this recording.